What about the mayonnaise though?
Yeah, I want to see the mayonnaise. You must show us mayonnaise.
Yeah, who wants the whole video?
Yeah.
You can watch the 30-minute video on your own.
Yes, the mayonnaise.
Extra heavy mayonnaise.
Here's the mayonnaise. It is very nasty.
Where's the ball?
Is this Bowler destroyed?
Yeah, why?
So the stitching came off,
Oh,
but the ball was fine. The stitching came off though. I think 2 reasons. 1, they hit it more dead center, and 2, the mayonnaise is a lot, right? It's contained, or it's a thick liquid rather than having air between each particle. So I think there's a bit more friction there that pulled off the stripping of the baseball.
So we made fire. We dieseled mayonnaise.
There's some flame happening right there.
Why?
The molecular interactions between this paper covering and the baseball.
So some thermal.
Right, so a thermal transition.
Thermal, so yeah.
Anyway, it's a fun channel. If you don't know Smarter Every Day, they do some really fun, crazy stuff.
Pyromaniac.
Does the fire
They made fire with a
the
baseball.
like
and
it
a-
loses kinetic energy or something like that?
There is a loss of kinetic energy there, yes. And they say later on that you can actually you can smell the mayonnaise burning, right? So there's a lot of friction happening in that transition. On the conservation of energy does not, but momentum, yes, right? So the same thing happening here. There's lots of, yeah, a lot of views in a week. Right, but again, this is illustrative of, right, what type of collision is this then? It's inelastic, right? It is not elastic. It is not elastic because there's energy the kinetic energy is not the same, but you have to do a lot of calculations here to.
Well, the fact that there's thermal energy there to begin with shows that it's inelastic.
Yeah. Yes. Kinetic energy is not correct because there's energy being transitioned into friction, heat, etc. All right. So open up. All right. So let's get on to some other. Oh, I didn't want to do that yet. That's okay.
It doesn't smell sweet.
Okay. So we're going to spend time on 2 more concepts. Specifically center of mass, and then we'll do a little rocket stuff at the end. Boo? Oh.
I know the rocket stuff isn't going to be on the module exam, but it's the center of mass stuff going.
Yes.
Oh, you speak from experience. It turns into liquid.
All right, so let's do this problem. Talk about our center of mass idea. This is actually a fun problem. So if you've noticed, or if you haven't noticed, I'm going to tell you now. In the textbook, there's 2 sets of problems. Well, there's like 100 problems for each chapter, but the first 60 to 70 problems are specifically problems about that chapter, and then there's 30 to 40 problems after that that actually bring in or have you access rather the toolbox that we've been building for the entire semester. So this problem is one of those that they include, which I think is great. So here we have a fireworks display. Have a rocket is launched from the ground with a speed of v0 and a direction of theta above the horizontal. So even before we go on to the rest, what type of object is this rocket? What? Oh, projectile. I don't. Doesn't matter. Good, so it's a projectile. How do we analyze projectile motion? Kinematics. Great, so I'm not even gonna do the rest of it yet, right? But this is a projectile motion where we have something going off at some initial speed. We have theta. So what's the path of the projectile look like? Good. Okay. So during the flight, then the rocket explodes into two pieces of equal mass. We'll get to there in just a second. For part A, it says, what horizontal distance from the launch point will the center of mass of the two pieces be after both have landed on the ground? So somewhere we have a anti-collision, if you wanted to call it that, where we have a piece of the firework go one way and a piece go the other way. Actually doesn't even specify what's happening to them. We actually don't even care what's happening to them, because what the center of mass tells us is that if we trace these objects and found their motion, we would see that they would still, or the center of mass of these would still follow this parabolic trajectory. So this is now the path of the center of mass, which means that this distance here that they want in part A is the distance that the center of mass would have gone. Or another way to describe this is that this will be the center of mass of the two objects when they reach the ground. So this center of mass is very useful that way, right? So we can describe the motion of these things based on what's going to be happening. So how do we find, this is now kinematics, how do we find this distance using kinematics?
Break it up into X and Y components.
Good, we break it up into X and Y components. Then what do we do?
Create our knowns and unknowns.
You find
Good.
time through the distance of
Good.
y, and then you apply that time to the distance of y.
Excellent, right? So we break up into components, identify what we know, what we don't know. We identify some zeros here. So this will be a 0 in Y and a 0 in X, or X and Y, rather. So let's do this really quick. So I'm just going to kind of go faster here, but hopefully we've seen this. Find X, base of X and time. Okay, so what is our, I'll turn on the light here in just a second. What's our initial X position?
0,
Initial Y position?
0,
Final X position.
0. No, duh. X.
Good, XEM, this is what we're looking for. Okay, what about our final Y position? Also 0, right? So we're coming back down to where we start. Okay, what's our initial X velocity?
VO. VO.
Good.
Cosine.
VO cosine theta. What's our initial Y?
VO sine theta.
Good. V naught sine theta. What's our final X? Good. Why is it the same?
Because
The acceleration in the X direction is 0. Good. We don't know time either. What about our final Y? We actually do know this one too. It's not 0. Right? Remember, as it's coming in contact with the ground, it's going to be the same, just in the negative direction as our initial velocity of Y, because we don't have air resistance and we're coming back to the same height. Good. And our acceleration in the Y direction? Negative G. So we have established that positive is up and to the right. Good. And again, the only thing we don't know here is time on the Y side. So we're going to start on the Y side and we're going to use what equation to get time? Think it through without me having to write kinematics down.
Probably the first one.
square root of t or T equals the square root of 2 times your distance over gravity.
Good. And yeah, I think we could use the first one too. I was thinking the second one. First one's great. All right, I'm gonna do the second one just because that's what's in my head. Good, our delta y is 0. We know this initial, we know this here, so we have 0 is equal to b naught sine theta times t minus 1/2 gt squared. What can we do with one of the t's? We take it out because we can divide both sides, but anyway, by t, then we bring over this negative b naught. This is a plus first, and then we plug in our ay, and then we get negative g. Yep. We have a negative 1/2 gt. The negatives cancel. And then we have an equation for time, which is we bring over the half, so we get and divide by 2, or no, we divide by g. So we have 2 b naught sine theta divided by g. I think that's what you said, Mary.
I had a square root in front of it.
Oh, I just had this,
Okay.
but we can cancel one of the t's, so we just end up with this. All right, now what do we use this t for?
In the X
We're still in
side.
kinematics, right?
Yeah.
Yeah, so this is all just a kinematics problem, this part A. So for x, we're going to use the second equation again, which is our final is equal to our initial plus v naught xt plus 0, because there's no acceleration in the x direction. Our initial position is 0. So then this just becomes our xf, which is our x center of mass, or the distance that the center of mass would have gone, is our initial velocity in x, which is v naught cosine theta times t. We now have t, so we end up with this great equation. Yes, it is great. V naught cosine theta, oh, I ran out of space. 2 v naught sine theta over g, sorry. Which goes to this equation here. We have 2 over g v naught squared cosine theta times sine theta. Okay, so that was just a kinematic equation or kinematic solution. Right, that's all that was. A projectile based on that info. Okay, so that's all that first part was. Hopefully that was a semi-good review that way. Okay, so now here comes the application to our new chapter. Okay, we all set with this? We good there? I know we went a little quick. Okay. All right, so now we have this xcm. So we have the distance that the center of mass would have gone. Okay. Second part of this question says, if we know that one piece lands a horizontal distance d from the launch point, where does the other piece land? Okay, so now we're told that this one piece comes and it lands, say here, where this is now a distance d from our 0 point. And we want to know where the other one lands. So if this d is here, where do we instinctively know that this other piece is going to go?
XCM plus D.
Good. Well, you're right. Not necessarily plus d, but on the other side of the center of mass, right? Somewhere over here.
So xcm plus xcm minus d.
We don't know that it's going to be d yet.
I mean, is it going to be the same, the difference between xcm and d, the other parts?
That's what we're going to find out. All we know is that it has, why does it have to be on this side? Okay, even besides that.
Because
Good. Good. All right, so if one piece lands here, then the other one has to land out here in order for that center of mass to stay there. Okay, good. So now we're going to do this.
So it will stay symmetric to the center of mass.
If we have a condition. we're going to solve it without that condition first. Okay, so we have this value. So if somebody wants to plug that in and get whatever number that is, then we can do that. I won't carry this with us when we do this next analysis. Okay. But now I need to talk to you about the center of mass and the equation we use for center of mass. That is defined as an R. So this is a position vector, which means that we have a 0 and it's pointing to that center of mass, which means that we could be pointing in lots of different directions, like a 3D dimension, right? What we're doing is we're saying, I want to find where that center of mass is, and that center of mass is going to be defined by how much mass, or some, we'll call it 1 here, a piece of mass that we'll call M1 has a distance from some 0 point of R1. I'm going to add that up to another piece that has a distance of R2, and another piece, and another piece, and I will continue to do that until I've added up all of the mass and the distance away from some 0 point that all of those masses are. But because I want distance at the end, I'm going to divide out the sum of all of those masses, or the total mass. So what this equation then comes down to is a summation of all of the masses at wherever they are located, divided by the sum of the masses. So this is what is called a weighted average. If you're wanting to calculate your grade, this is how you do it. You have a certain weight for a given piece of your grade times whatever value that you got, plus whatever weight times et cetera, et cetera.
So the weighted average is basically to account that mass and the two objects that they're going their separate ways. There's some masses going to different masses or objects in some place.
Yes, right. And so that center of mass, once it breaks up, we can track that center of mass. And that center of mass will always be the center of where those objects are.
Quick question, can we get a negative mass to account for something, I don't know.
We could get not a negative mass, but a negative R, depending on where our 0 is.
So
Yes.
Your 0 is where the rocket started off as, not. the
Correct.
center.
So here our 0 is where the rocket starts.
Okay.
And this XCM, which is now our center of mass, has some value with respect to that 0. But yes, precisely correct. It depends on where we put that 0 point. Yes. A sub I, meaning for each of these, so this I is equal to 1, which goes to n. That's how our sum sign goes. All right, so what we want in part B is we want to know the distance for these other two. And those masses have landed, which means that we have a one-dimensional thing. So we can turn this vector then into x, right? We now have this position in the x direction because we're only along that x line. So we don't care about what's going on in the y or the z. So that means that we can define our XCM, or the center of mass of our rocket, firework rocket, is equal to one part of its mass, m1. And what's the distance that that m1 is at? D. Good. That's what we're given here. Right? It's some distance from our starting point. Okay, we then have a second mass that we don't know what we're looking. Oh, wait, did I say D? Oh, I'm sorry. I'm mixing up my D's. Oh, no, that's fine. We'll call this one X2. And this is the one that we don't know. All right, we don't know this one yet. That's what we're looking for. Then what do we divide this by?
1 plus M2.
Good, total mass of the rocket. So if we know our masses, maybe we don't even know our masses. In this case, we do. We know our distance that the first one lands, and we know our center of mass distance, which we found here. We now have enough to find X2. So how do we rearrange this? Good. Good. All right, so we have our sums of mass times our XCM, M1D plus M2. So to get that by itself, we're going to bring over, we're going to subtract our M1 and then divide by our M2. So we get something that looks like this. That is our equation for the distance that the second one is at. Now, in this case, the masses are the same. So if M1 is equal to M2, what happens now?
Cancel out the denominator.
Good, right? So this turns into 2M or 2M1. This one's just M1. This one turns into M1, which means our masses cancel out. So we're left with 2 times the center of mass minus the distance divided by 1. 2 times the center minus d, and that's then our equation. Okay. But before we make that assumption, we have things dependent on the masses and their distance with, or just the relationship with that distance. Okay, so that's how we're going to use the center of mass. We'll typically look at just one direction, but we won't go to 3 directions. We may go to 2. But if we go to 2 dimensions, because it's a vector, we have to split things up. So we can go and analyze things in the x direction, go and analyze things in the y direction. Then we have an xy point for that center of mass. Okay.
Just now.
What's that?
Are we doing that just now? Or
No, in this case, we're looking at the x, just looking at this horizontal.
but they would theoretically land and y equals to 0.
Correct. So the center of mass in the y direction is at 0. So I guess you're right. We did it in y as well, but we only cared about this. Once they landed, we only cared about these r's. So this is RCM, or no, that's R1.
Yeah, okay, that's a good question. Sorry.
Oh, that's okay. It's fair. All right, other questions with the center of mass? Yes.
If I were to split into different masses, this would look a lot different.
Well, if it was more than, well, at 2 masses, if the masses were different, then this would be the equation.
Okay.
If there was a third mass, then we just have to add on, where we go? We'd add on another mass here. But we'd have to know at least one more piece of information in order to then solve for this, right? We have to know where that other piece fell. But we would just keep adding on masses and the distances that they fell at.
And it's in respect to the launch point.
Yes, in this case, our 0 point was with respect to the launch point. Sometimes it's useful to put your 0 point at the CM. Right, and if you do that, then you could define where those different distances are at. Yes.
So if, say the 2 pieces both broke into 2 more pieces, the center of mass of those pieces would be parts on this one, like the 2.
That's a really interesting question. So you're saying if each of these broke into 2 more pieces, then you could, so the center, good question. So the center of mass would still hold for the whole thing, but you could do another analysis based on this center of mass for this one and that center of mass for that one. Totally. That's actually really cool. Good. All right, and again, oh yes, sorry.
Fine. If you set your center of mass to 0, wouldn't
Yes.
that mean that one of the position vectors would be negative?
Yes,
One would
very
be on
good.
one side, the other one would be the other.
Correct. So if we reset this to be 0, Let's just draw it. All right, so this is our center of mass. We're now resetting this to be our 0 point, right? And this is D, well, we'll say X1 here, position of this one. So now if this is our 0, we're now looking for this R for 1, which is going to be a negative.
But if you're given one R and both masses, you could set X to be, or the center of mass to be 0 and then find the other R.
Yes, that's perfect. Yeah, so again, we can move around the 0 point, but we want the 0 point to be where we have enough information to solve the problem. Right here, we would, because we know this distance here, and we know this distance, then this then just becomes XCM minus D, just in a negative direction because it's pointing away from the center of mass. And that just helps us because once this is 0, then, oh no, this is 0, then we move this to the other side, so that takes care of the negative there. A good question. All right. Got 15 minutes to do rockets. So again, there's a mastering physics piece that is that will open for you. That is all rockets, but rockets are not on the quizzes or exams or things, but they're super cool and we like them. So, and I have my notes today, so I don't mess up. All right. So I don't know how else to do this except to actually go through the derivation to show you how cool it is. So we're going to do, this is a full physics derivation here for you, which we haven't done a whole lot of. So I guess if you want to fall asleep, now's the time. All right, except it's rockets, so you don't want to fall asleep. All right, so here we go. So here's my rocket. I have a rocket that is given with a mass of capital M. Attached to that rocket is some little piece of fuel that I will call delta M. And this rocket is moving with a speed of v. Okay with that? Not too complicated. Then at some point later, I still have my rocket moving with some mass of m, but now this delta m has detached. And because it has detached, I now have a velocity plus what I call it, plus a little velocity. And this little mass actually has some velocity that we will call v fuel. Meaning if you're sitting back and watching this rocket that's out in the middle of space, so there's no external forces acting on it, you see this mass have a velocity that's still moving down. So because this is a system with no external forces, we can talk about what conservation law? Momentum, right? This is kind of our reverse collision idea, right? So what is our initial momentum? Right, so we're going to be talking about our initial momentum equals our final momentum. What momentum do we have to start with?
Delta M plus M times V.
Good. So we have the combined mass moving at our initial velocity. Good. What momentum do we have at the end?
Mass times V plus delta V.
Good. So we've got mass times our initial velocity plus this little velocity. And we have our little mass times the fuel that mass is going. Okay, we're going to then distribute these. So we get m times v plus delta m times v, m times v plus big M times delta v plus delta m v fuel. What can we do here? Good. So we have this one on this side and this one on this side that are the same, so that goes away. All right, so now we have delta m moving at our initial velocity times a rocket moving with this extra velocity plus a little m times the fuel's velocity. All right, have I messed up yet? No, I've not. Okay, good. All right. So at this point, we're going to invoke relative velocity that we talked about at the end of chapter 2 or 3. I don't remember which one it was. Specifically, we're going to introduce another idea or another velocity here, which we will call EX, or the exhaust velocity, or the velocity of the fuel with respect to the rocket. So that is defined then as initial velocity, or the velocity of the rocket, minus our fuel. Or again, the speed that the exhaust has with respect to the rocket. Or we could rearrange this so that we can rewrite this as our fuel is equal to our V minus this relative velocity. And what we're going to do is substitute this relative velocity in.
That is a relative velocity to what is that
Between the fuel and the rocket.
in the first stage?
We don't have any stages happening yet. But
So
sure,
before they detached,
yes, once the fuel is detached.
after they detach.
Yes, after they detach. All right, so if we substitute that in. I'm going to distribute that one more time. So we get delta mv is equal to m delta v plus delta mv minus delta m dx. And what's happened? What can we do now? Good. That's the same. So now those can go away. If I then bring this to the other side, we get this relationship here, which is fairly simple if we think about it. We're losing some amount of mass. That mass has some relative velocity with respect to the rocket. That sum, right, this is an m times v, is equal to the mass of the rocket times the additional speed that that rocket gets. Okay, so I'm going to take a little side trek here. What if we divide both sides by delta t? Or, I guess that's actually very interesting. Yes, it is. I didn't think about that. So we're going to distribute this delta t just to make it look a little. So now we have delta m over delta t, v times ex is equal to m times delta v over delta t. What is this? This is acceleration. Delta m over delta t v dx is then equal to mass times acceleration. Mass times acceleration, if this is the only, well, this is m times a, we introduce our Newton's second law. This is now a force of thrust that is coming from what changing?
Change in mass.
A change in mass. So if we change the mass fast, if we have a lot of mass that we change in a slow time that expels very quickly with respect to the rocket, we get an acceleration, or we have a thrust from the fuel. Cool, huh? All right, so back to this. We're now going to invoke a couple things. Here's what we're going to do. We're going to say we're going to limit this delta v. We're going to make it really small. So small it's going to be infinitesimal, so we're going to call it dv. And that is an increase in our speed. we are then going to define our delta M, and I guess we need to do that over here as well, as being a negative dm, because this is a loss of mass or a decrease in our mass. Okay, if we do that, run out of board space. We can then rewrite that equation to be dm dx is equal to m dv. Oh, thank you. It's right there. Ooh, that thing. All right, we're going to now divide over our m. I'm going to rearrange just slightly. So we get this. At this point, we now have two constant, well, no, this one's not constant. We now have a constant times this mass and this velocity. So we are now going to integrate. Let me pull that up. 1 over m times dm and integrate dv. If our bounds are from some initial mass to some final mass and some initial velocity to some final velocity, this then becomes what? How do we integrate 1 over x? Natural log. So this is then the natural log of m final minus the natural log of m initial is equal to v final minus v initial. We have a negative here, so we're going to distribute that into the natural logs. We get natural log m initial minus natural log m final. And how do we combine natural logs? We will divide here. So this is v sub x natural log m initial over m final is equal to plus v initial is equal to v final. This is the rocket equation. This tells us that if we have a relative velocity between exhaust and the motion that we have of the rocket initially, and we have some change in mass happening, that we will then end up with some final velocity. Right? So we can use this relationship to talk about mass and acceleration and thrust. And that's what makes rockets go. Is how fast can you expel, right? This delta T here. How fast can you expel the mass? How fast can you have a change if you have a large change in mass over a short amount of time? And that velocity comes out very quickly with respect to the rocket, then you will get an acceleration of your rocket. Right? And that's all pinned on this idea of momentum. And the idea of momentum coming from our second law that tells us that we have a change in momentum over a change in time, where this momentum is now mv, where that m is allowed to be variable. Right? You decrease t, you have a high mass change in a short amount of time, and you get a large thrust or a large acceleration or a change in your velocity. So then we can do problems that look like this, that we don't have time to do. Like this one, an astronaut floating in space in a manned maneuvering unit, which I guess works, where you're given an acceleration when one of the thrusters is fired. You are then given the relative speed, and then you can find the change in gas, change in mass of gas over time. You can then find the thrust of that, right? So this is basically Wally with his fire extinguisher,
Oh.
I think that's
right?
the
Same
Martian.
thing. What?
The Martian.
Where he punctures the hole.
No,
Oh, yeah,
like
that
the
too.
actual like
I've
vehicle.
more recently watched
Oh.
Wally with children. Martian. But Yes, the same, good, same concept, right? If you are changing mass and you're changing mass fast, then you will have, and you have a velocity relative to another, then you have motion. Where's the other one? Oh, I guess not, maybe it's on the next page. Oh, I guess that was the only one I had on here. So that's rockets. Yes.
Will we be doing these types of things in the next module?
Will we deal with them? No. So the rockets is kind of just an extra added bonus that is too cool to not talk about. All right, and it's the application of the momentum, not only changing velocity, but also mass. All right.